Okay, for the enhanced DS, first we have to elaborate the key generation. With this algorithm, we can create a key, two keys of 10 bits, and we can change the bits to see that it works.
One, but
One.
it becomes two of 8.
One divided, yeah, into.
Which is
Change the bits, so we can just one bit.
so we can see.
Yeah, you can pause it to see that it matches. And for the next part of the algorithm or the enhanced DS, we have to create its initial permutation. That what does is changes the order of the bits of the first bit with the algorithm of the bit of the key generated before.
Yeah.
It follows the algorithm seen in class, the ciphertext, the initial permutation algorithm. Arriba, it's yeah. Yeah, the ciphertext, the initial permutation. And then, well,
we also have
más abajo, ¿no?
the inverse permutation.
The diffusion, ¿no? Okay.
No.
No, the inverse,
Which is here. Then we have this. Can you see my screen? Yes.
Mm-hmm. ¿Qué no vas a hablar tú?
Okay. Well, then we have the expansion with the XOR, which is basically this. We take the key and we arrange it this way. I mean, not the key, the plain text, the left half. I mean, no, the right half, which is part of the f function. So here we take the right half and we arrange it in such a manner, and we expand it to 8 bits, which we XOR with the first key in the encryption process. Yeah, with the first key. And then we have the shift boxes, which are used to create diffusion, and that's basically here, PS boxes. And what we do is we take the first and fourth elements for the rows in both the first and the second S boxes, but from different from the two different rows that we get, and then we take the columns, which are the second and third for each, and whichever number we get from that, which we pick out here, we turn it into binary form, and we do the next permutation, which is P4, and then we just gotta do the SW function. Like that's the F part. So basically we XOR, we expand, we XOR, and with the S box, and then we shift left and right. Well, left with right, and basically we can see that here. We can, even take this as a key. Now that we've changed it, but where's key 1? Oh yeah, key 1 changed, so because we defined it here. So this did change too, but here is the process altogether. So basically the key preparation, and then this whole thing, which is this function, which we can pretty much see here. This is the entire function, and the decryption process, which is the same, but we switch the ciphertext for the plain text, and the two keys, and you can see that that's the case here. Like here we had in the first part the first key and the second key, and here it's the opposite. And here we can test that out. We can switch this key, for example. I mean the plaintext and the key. And as you can see, the plaintext is the same plaintext that comes out here when we we basically encrypt it, and then we take the whatever comes out to decrypt it, and it's the same. And then for the next part, which is what makes the enhanced DES different from the not the enhanced DES, the enhanced simplified DES. Like what makes it different from the simplified DES is that we basically have this before everything in the encryption process, and we have that after everything in the decryption process. So we're gonna use the simple columnar transposition technique to not diffuse but permutate the values, which is a problem of this algorithm, because because you're not using any sort of diffusion. You could technically do a cryptoanalytical attack in which you map the frequency of the certain bits that reoccur. Say, if we guess correctly that each letter corresponds to 8 bits, we just need to map all, to split the entire ciphertext into 8-bit parts and see what occurs the most. So, but that's getting ahead of us. So first we make the square. To be able to make the square, we need to define how many letters are missing to create a perfect square. So say we have, I don't know, 22 letters to create a square, we need 3 more. What we add here is some padding right here to be able to do that after finding how many letters are needed. And then we put this into matrix form right here, and we select how many rounds we're gonna transpose it and switch it, like switch everything. And for that we create some random values to be able to switch each of the columns, and every time we transpose it. So basically the number of rounds is how many times it's being transposed, and the letters are being, I mean the columns are being switched. And then the decryption process is basically the same. It just takes this list that we randomly created and it puts it in reverse order, and we do it for however many rounds we made it initially. And then, well, everything else is basically just mapping the matrix to a string, and then from a string to binary for the encryption, and from binary to string in the decryption process. And the enhanced DES is basically first the creation of set boxes and the transposition. Well, first, yeah, that, and then string to binary, and then for each block of 8 bits, which are here. So the first part is that, then binary to string to binary, and then those 8 bits are each encrypted by the simple DES, and that's what's being returned. And the enhanced DES decryption is the same, just in reverse order. So first we take the ciphertext, split it into 8 bits each time, decrypt that, and then we convert that to actual string, to an actual string, to actual characters, and then we just transpose that however many times in the order that was provided. So for example, we can do we can take whatever key you want, and we'll need this. Oh, this is a very long string. We can take something a lot shorter. You know what? I'm gonna just delete that. Hello world. And we're gonna encrypt that. We can use, for example, 3 rounds, and well, that prints hello world, but we can also print the ciphertext and the random order that was used. This is the ciphertext, and this is used as input to the encryption process. And what we did is since we used ASCII, we can even have spaces, and the padding will be more spaces. So that's the padding right there instead of X's. We thought that would be an enhancement to the way it was being proposed, but that's aesthetically, but it's not an enhancement at all with security wise. But we can have any size string. We can have A, B, C, D, E, F. and we can encrypt that. We can see that it's using a 5x5 block, which makes sense since, well, there's 25 letters. I don't know, I think I skipped one.
No W.
Okay, okay. If I put the W, it's gonna make it 6. Wait. Yep, it makes it from 0 to 5 it's 6, so it makes sense. But yeah, it's 25 letters, so the box must be 5x5. And this is ciphertext. And then we print the enhanced decryption, which takes the ciphertext, the random order, which can be considered a second key in this case, and we decrypt it. Is there anything you want to add, Julio? Nice. All right, then I guess that's it. The code is in GitHub, and yeah, feel free to ask any questions if anything doesn't make sense or.
And they were developing Jupyter with Python, right?
Yeah.
And yes, it is in GitHub, and this video is in GitHub too.
Exactly. Thanks for watching. Like, subscribe, and all that.
See you guys in the next.